Hello to everyone. Myself, Dr. C.R. Kesavulu, Associate Professor, Department of Physics, Institute of Aeronautical Engineering, Dundigal, Hyderabad. Today I am going to discuss about this is the one of the last topic in the laser glass spectroscopy, European 3 plus dope silicoborate glasses for red laser and scintillation applications. This is the one of the important topic in the laser glass spectroscopy. This is so outline of the today talk is on the introduction and experimental methods and techniques and results and discussion and conclusions. These are the last topic in the European 3 plus dope silicoborate glasses for red laser and scintillation applications. So introduction or motivation of the rare earth elements. Among the periodic table, we are going to discuss about the lanthanide ions, particularly in the European 3 plus. That is the lanthanide elements of this atomic number is 63. In this among the 14 lanthanide elements, we are going to discuss in the European 3 plus dope silicoborate glasses to study the applications of red laser and scintillation applications. So these are the importance of lanthanide ions. This is the fascinating of optical properties, luminescence from the FF transition, and the characteristics of emission of each rare earth elements, and narrow emission lines, and chromatographic purity. Emission color is not very dependent on ion environment. Large Stokes shift is observed, and direct excitation in 4F levels is not efficient. Sensitized luminescence is preferred, and long excited state lifetimes. These are the fascinating optical properties involved in the rare earth doped laser glasses, and the shielding of 4F orbitals and similar chemical properties, electrostatic bonding, variable geometry. So these are in this figure shows the visible emissions and near infrared emissions. Particularly European doped glasses, it exhibits the red luminescence, that is nearly in the visible region around 632 nanometer. We are exhibiting the red light. That is why European doped glasses used for the red laser applications. At the same time, the scintillation applications are useful for the European 3 plus doped silicoborate glasses. This is the introduction of rare earth elements. This is the 4F and 5F black elements are their unique trivalent state of 4F electronic seated by the 5s2 and 5s6 electrons, and so many advantages. Glasses is an interdisciplinary photonic platform material due to its high optical transparency and thermomechanical strength and ability to be shaped into almost unlimited range to geometrical structure and composition. Applications is laser gain media, fiber amplifiers, optical components, medical accessories, and massive structure and entertainment, etc. So mainly in rare earth elements, main application is laser gain media, optical fiber amplifiers. These are the important application in the rare earth doped glasses. Next, introduction. Particularly in the scintillation applications, the glass material doped with rare earth elements are drawing attention as scintillators, amplifiers, and fiber laser materials. So scintillating glasses doped with rare earth elements have become a viable alternative single crystal in the field of solid state scintillation detectors because of the low cost and easiness of the manufacture in the large size. So we can study the large size within the economically cheap low cost. We can use to study the glass materials. That also it is particularly in the solid state scintillation detectors applications we are using for the European 3 plus doped silicoborate glasses. Because scintillation applications, the main important parameter is required is high density. So which material it exhibits the high density and high light yielding and fast decay times, and most important properties for scintillation glasses. So scintillation glasses is mainly three important parameters is important. One is high density and high light yielding and fast decay times. These are the most important properties to study the scintillation applications in the particularly in the glass materials. So scintillating glasses with a different doping with improved properties and suitable for the electromagnetic and hardened calorimetry can be developed by using the scintillating applications. Is one of the important applications for the hardened calorimetry can be developed by using the high density and high yielding doped glass materials. In this study, we prepared different rare earth doped lithium based calcium silicoborate glasses and characterized their absorption, excitation, emission, and X-ray induced luminescence and decay time measurements were studied in the present European 3 plus doped silicoborate glasses. Next, European 3 plus doped glasses. Among all the lanthanide ions, europium is the best candidate to use to spectroscopic probe to investigate local structure around lanthanum ions and condensed matter. This is because the lower lying energy level of the European 3 plus ions simple and transition between the 7F0 to 5D0 level non-degenerate level is convenient to apply the fluorescence line narrowing technique to analyze changes to site through energy level scheme analysis. Also, European 3 plus doped materials are frequently used in photonic applications as a red emitting phosphorus for field emission technology due to the narrow and monochromatic emitting nature of European 3 plus science due to the 5D0 to 7F2 transition that is mainly involved in the European 3 plus doped materials. This is mainly useful for the red emitting phosphorus also we are using for the European 3 plus doped laser glasses. This material selection in the present material is European 3 plus doped silicoborate glasses. This is used for the red laser and scintillation material applications. So we are choosing the chemical composition is 55 minus X mole percent boron trioxide B2O3, 10 mole percent silicon dioxide, 25 mole percent of yttrium oxide, 10 mole percent of calcium oxide, and X mole percent of europium oxide. We are varying from concentration is europium is from 0 to 2.5 mole percentage. These are the glass preparation synthesis or fabrication of glass material were fabricated by using the conventional melt quenching technique. We are taking the bench composition is 8 to 25 grams. So taking the above mentioned chemicals, we are put into the agate mortar and crush the chemicals as a fine powder. Then after taking the fine powder, we put in the platinum crucible and we are put into the electrical furnace at the temperature of 1060 degrees centigrade for 90 minutes. Then after melting the glass sample, we have pour into the preheated brass mold at the temperature of 350 degrees centigrade to avoid the thermal stress and strain and cool down to the room temperature. Then take it out the prepared glass sample to cutting and polishing. After cutting and polishing, we are sent to the calibration purpose. First, initially, we need to measure the XID profile. So, by XID profile, we have to whether it is a glassy nature or crystalline nature. It is observed to prepare the glass sample. It shows the crystalline nature or amorphous nature. Finally, we are confirmed with the XID profile. So, XID profile, we are observed that all the observed peaks are broad bands only, broad bands. That is why it shows the glassy nature. The prepared samples are shows the glassy nature. Next, coming to the experimental technique and methods calculations. So initially, we have to measure the X-ray induced luminescence spectra and optical absorption spectra by using the Flickr Link spectrometer. The fluorescence and lifetime measurements, we are using the Jobin Ion Fluorolog 3 spectrophlorimeter. So all the above measurements, X-ray luminescence and absorption spectra and luminescence and lifetime measurements were carried out. All the measurements at room temperature only. Next, coming to the optical absorption spectra of the European 3 plus doped silicoborate glasses. From the optical absorption spectra, we have studied the optical absorption spectrum wavelength versus absorption coefficient in alpha. See here, optical absorption spectrum shows the from scanning from the 350 nanometer to 2450 nanometer. Among the all the absorption bands, starting from 7F0, European 3 plus size, the ground state is 7F0 to different excited states. So from the absorption spectra shows in figure, it is clearly shows that the 5 absorption bands are being observed in the UV visible region and UV ultraviolet and visible regions, and 2 more bands we are observed in the infrared region. That is 7F6 and 7F6. 7F6 means it is 7F0 to 7F6 and 7F to 7F6. These are the NI region we are observing. So from optical absorption spectra only we are calculated the JO parameter, that is the intensity parameters of omega 2, omega 4 and omega 6 and radiative lifetime and trend how follow the omega parameter trend. Omega 4 greater than omega 2 and omega 6 in the present study. That is the omega 4 value is higher than the omega 2 and omega 6. That is in this present study we are studying the tau radiative is the 4.78 milliseconds and red value, that means R means the red luminescence, that is we are tuning the red luminescence by using the 7F0 to 7F1 to 7F0 to 7F2 level, that we are getting 2.98 value. From the absorption spectrum of the 0.5 mole per European doped glass, the oscillator strength we are calculated by using the reference number 7 and the JO intensity parameters we are calculated by using the reference number 8 and 9, and we are found that the omega 4 value is we are getting the higher value compared to omega 2 and omega 6. There is higher rigidity of the medium and higher covalence around the European 3 plus ions in the ground state and excited state. See JO parameters, you have studied the thermal correction and without thermal signal with thermal correction, and the emission spectra. By using emission spectra also we have calculated the JO intensity parameters, and excitation spectra also used to calculate the omega parameters are omega 2, omega 4, omega 6. So these are the they are calculated by using the absorption spectra as well as emission spectra and excitation spectra. This is the excitation spectra of the European 3 plus dope silicoborate glasses. We are pumping the mounted in the 613 nanometers, and we are getting the different excitation bands. The excitation spectra of the present glasswork is obtained mounted in the emission is 613 nanometer. From the figure, the excitation spectra high energy transitions have been located and assigned as a 7F02, 5D4 and different excitation levels. Among these levels, this is 7F02 5L6 transition is found to be most intense, which will be excited to record the emission spectra analysis. So, emission spectra analysis we are using to 5F0 to 5L6 because it's having the highest excitation wavelength. See the emission spectra we are monitoring that is we are exciting the 394 nanometer, and emission is we are getting the 613 nanometers. That is among the emission spectra, the wavelength versus intensity. We are observing the different emission spectra of the European 3 plus doppler glasses. In this particularly, we are getting 5D0 to 7F2 transition is the highest intense transition. That is useful for the red laser applications we are using. So obviously, the emission intensity of observed transition increasing with increasing of European 3 plus ion concentration. We are increasing the concentration, the luminescence intensity will be increasing. So the room temperature of emission spectra of the 5D0 to 7F2 transition is the very high intense transition. That is why it is useful for the red laser applications. Next, this is the X-ray induced emission spectra. This is a very important property to study the scintillation applications. So scintillation applications, it exhibits the X-ray induced emission. So increasing the concentration from 0.05 to 2.5 mole concentration, increasing the intensity, automatically X-ray luminescence also increasing from concentration 0.05 to 2.5 mole percent. Since the energy of X-ray is higher than that of the excitation energy of the European 3 plus ions, the X-ray excitation was initially appeared at the base of host glasses, and energy was later transferred from European 3 plus ions. So this is the X-ray induced emission spectra. So almost emission spectra and X-ray induced emission spectra shows the both exhibit the similar emission transitions, particularly 5D0 to 7F2 transition is the highest intense transition. And lifetime measurements and decade time measurements were carried out European plus doped silicoborate glasses. The experimental lifetime, the decay rates of 5D0 level, the 5D0 excited level of the European 3 plus ions. We have studied the 0.5 mole glass. So this 0.5 mole glass, we are monitoring the emission is 613 nanometer, exciting is 394 nanometer. So here the experimental lifetimes is measured. These lifetime measurements were starting from the low concentration. We are getting 1.85 millisecond to 1.77 milliseconds, which is almost independent to the European ion concentration. This shows that the probability of non-reactive energy transfer between European 3 plus ions glasses is negligible. The experimental value calculated by using this formula. This is the partial energy level diagram of European 3 plus doped BSYCA European glasses. The energy transfer we are observing this energy band gap is nearly this 2,470 centimeter between this from ground state to excited state level will be well matched with the band levels. That is why the energy transfer takes place in the European 3 plus ions. So this is the partial energy level diagram of European 3 plus doped silicoborate glass. So finally conclusions. So conventional melt quenching technique used to study the European 3 plus doped Eu3 and calcium silica borate glasses. We have studied the physical parameters as well as spectroscopic parameters. Relatively high value of omega-2 value suggests that higher covalency between the metal ligands bonds as well as higher distortion in the symmetry of European 3 plus in the glass matrix. Emission probability and stimulated cross section and experimental branching ratio, optical gain bandwidth were also calculated by using that value is 280 second inverse and 1.39 into 10 power of minus 21 centimeter square. The branching ratio is 0.62 and stimulated emission cross section is 16.0 10 power minus 20 centimeter cube. These are the important spectroscopic factors. Next, the decay rates of 5D0 level is found to be first exponential for all the studied samples, and it decreased than the increasing of European ion concentration. Results of the present study suggest that the European 3 plus doped silicoborate glass could be potential candidate in red laser emission at particularly 613 nanometer, as well as it will be useful for the display device application as well as scintillator application. These are the conclusion and summary of the present European 3 plus doped silicoborate glasses. So these are the references cited in the present work. Though this paper is published in the Journal of Rare Earths in the 2018. So in this paper, we have studied the European triple doped silicoborate glasses. Mainly, it will be useful for the red laser applications, particularly the 613 nanometer red laser application. At the same time, it will be useful for the scintillator applications. So these are the last topic in the laser glass spectroscopy. Thank you. Thank you once again.
Like, share and subscribe. Hit the bell icon for more updates.